I want to welcome you to the Black Belt track. We have two great speakers today. Arun and Bob will be talking about Java in a world of containers. Would you help me? Give a big warm applause.
All right. Thank you so much. Can you guys hear me at the back? All right, awesome. Well, this is one of those unique, weird sessions where you see a speaker from Amazon and Oracle speaking together. But why it matters, because Java is the biggest enterprise languages, hands down, and Docker has changed the way applications are being built, and it matters to both of our customers.
Absolutely.
Yeah, my name is Arun Gupta. I'm a principal open source technologist at Amazon. I'm responsible for the open source strategy at Amazon.
And my name is Bob Van Det. I work at Oracle. My mission at Oracle is to make sure that Java runs great in the cloud, in containers, and especially in Docker.
Awesome. Let's get started. Now, that's a Bob slide.
This is an Oracle requirement. Don't make any decisions on anything that hasn't been released. Next.
So in terms of the agenda, we're going to talk about how do you build your Java applications in the world of containers. Then we'll talk about creating Docker images, some anti-patterns, design patterns, some to-dos, some not to-dos that we have seen in our customer base. We'll talk about how do you create custom JRE, how you can cut down that big 600, 800 megabyte image down to a small image as well. And then some of the cool work that Oracle has done in the land of creating those Java and Docker images in a very optimal way. So let's get started. In a world of containers, if you take a look at the reason we get into containers is some of these basic common premise. We look, safety and security is very important. I mean, at Amazon particularly, safety is the truly job zero for us. We look at it at the very top level thing. So when you're building in the world of containers, you don't want those applications to really be able to interfere with each other. And if one application goes rogue, you don't want that application to affect other applications. You want a mix of applications, not just Java, but you really want that polyglot architecture, polyglot operating system. So you want to have that ability that each container that is running for that application could be configured to meet the demands of your application. So that is a very typical expectation when customers jump on the journey for containers. If you take a look at Java in the world of containers, yes, there are a lot of languages, and containers do bring you up to a level where it becomes language independent, operating system independent. But Java already offers a lot of those advantages. For the longest time, I've been saying that Java gave us Vora, which is write once, run anywhere. Containers gives you Poda, which is package once, deploy anywhere. So it really takes that Vora premise and brings it up to the next level where it makes it language independent. But if you look at Java by itself, it gives you the ability for being hardware and operating system agnostic. You got the JVM running. It understands the bytecode. You just compile to the bytecode, and you're up and running. It gives you the safety and security. It uses by hundreds and thousands of enterprises across the world by some of the most mission-critical systems. They are running it in full production mode. Reliability, again, there are known issues with the language, but they are known, and then you can work around them, and then you can work with them. One cool thing that we're going to talk about today is runtime adaptive. Java works very well at the host level, where we understand how much CPU and the memory the host is offering, so you can adapt your application to the JVM accordingly. But come the world of containers, it introduces a new unit on the operating system. So what is the work that is being done in the Java language to make sure it is adaptive? As the containers are growing and shrinking, is the Java language really understanding those semantics? And of course, we all know all other languages are probably envious of the rich ecosystem around the Java language itself, in terms of testing, in terms of monitoring, in terms of scalability, in terms of libraries, in terms of frameworks. So there's a very rich ecosystem around it.
Yeah, as Arun mentioned, the fact that we're taking care of the runtime adaptiveness in a container and all of the features that we're going to talk about today, Oracle is committed to making sure that Java runs great in these container deployments. And we were asked to kind of give a personal view of Docker and what it does for us. And for me personally, obviously Oracle is using Docker in the clouds and many of its cloud products. But for me personally, I love the fact that I can have all these pre-canned images. I can test Linux Ubuntu's and Debian images, all even on my Mac because they've got a great Mac version of Docker. So we can do a lot of testing simply by just grabbing a container, bringing an image across, and running it. So that's what it does for me personally.
Just like Bob, we have lots of customers, at Amazon who are running containers in the Amazon cloud or AWS. And so, I do work with a lot of those customers to help them go into production. But personally, I love, educating. That's sort of my big thing on my personal side. So I help developers and customers understand how to build modern containerized applications. I've authored several books, several online courses. That's another way by which I educate in a much more scalable way. The customer interaction, the developer interaction is very one-on-one, very high touch, very valuable, but the scalable way is very important as well. And the fun part being I'm a Docker captain, so it gives me the bragging rights and some cool swag. So you can see me wearing my hoodie with a custom name kind of embroidered on it. So let's get into the meat of it. How do we create Docker images? Well, there is, of course, a Docker file that you need to create an image from. You have a directory, and the directory is sort of the context that the Docker CLI sends to the Docker engine when it wants to build the image. So in the directory, ideally, you should have just a Docker file. And if you want to build with JDK, you cannot use a JDK at a runtime. Typically, customers don't use JDK at the runtime or from the Docker Hub into production. So what they would do is they would download the JDK into their local directory, and then they will upload that Docker as part of the Docker file. They'll upload that JDK into the Docker image, and then they will have their Hello World class as well. So a very simple Hello World if you want to get started with Docker and Java here. Now, I remember being in part of a workshop, and a customer was saying that, oh, you know what? It takes forever for us to build our Docker image. Well, guess what? They had their entire Docker file and other libraries and class files in the root directory. Now, when the Docker CLI is talking to the Docker engine, it's sending the entire root directory as the context. So the pattern being here, make sure you create an exclusive directory, put your content only that you need over there. You can also look at things like .docker ignore. That's a file that you can add to your directory, which is very much like git ignore, which will start excluding the files that should not be sent as part of the context. That's just one of the cool tips that I've seen on how you can be more effective in building your Docker images. If you look at the Docker file contents here, then of course you need a base operating system. And all I'm doing here is I'm adding from my local context the JDK download to OPT JDK. Then I'm setting up an environment that this is my path, and this is where my Java home is going to be. I copy the hello directory. Notice the difference between add and copy. And that is a subtle difference. In terms of add, I'm saying add the tar gz to OPT JDK. One of the side effects of add is it automatically untars and gunzips for you. So that's pretty cool, because now I can just point to a tar gz, and it'll just do it. And I can do this with a URL as well, by the way. In case of copy, there are no side effects. It just truly copies from your local file system to the image file system. And then finally, I'm saying, all right, this is my CMD. Docker containers do one thing and only one thing really well. You may have multiple CMDs, but in this case, I'm saying Java, my class path is current directory because that's where my hello directory is. And then I'm saying, show me the version of the runtime and execute the class hello world as well. So it's as simple as that. I mean, that's a very simplistic thing. A lot of things that we can play around with it, and let's take a look at them one by one. Now, in terms of Docker image creation and execution, what do? Well, we say Docker image build. Typically, I've seen people use an old version of the commands, but Docker has this nice CLI which has these segregated commands like image or container. So highly recommended to use those newer commands. So in this case, I'm saying Docker image build -t. I'm tagging the image as dockercon, and I'm giving dot, which is my context essentially, which is sort of the entire context sent to the engine. So remember the docker ignore, how put all your files that you need in a separate directory, very critical. So it's sending the build context, it's taking, hey, it's 355 megabytes for context. I'm going in there. It shows you the complete step, 1/5 and so on, and then it builds the image. Well, once you have built the image, then you say Docker container run. Once again, Docker image and Docker container, the commands are very segregated. I run the command, I remove the intermediate layers, and I say run the image with the tag dockercon for me. So this works out. it just prints hello world, and of course, prior to that, it prints the version as well. It's very simple Docker image creation and execution. Let's take a look at it, how we can start optimizing this a bit more now. So we're going to start creating custom Java runtimes, OK? Now, if you take a look at JDK, it's a large download. And it includes packages like Corva. When I joined Sun Microsystems back in, well, a long time back, I was hired as a Corva test engineer. I don't know, how many people use Corva still? A handful. And it's OK if you're using it. I mean, there is a business need likely that is serving it for you well. But most of the time, when you're building the containerized applications, you may not need Corva. You may not need things like JAX-WS. Maybe you're using RESTful web services. You may not need management utilities. So JDK is a big bundle. It's got a lot of rich functionality, but you may not need all the components of it. JDK 9 introduced this concept of modularity, where the whole JDK and JRE were split up into multiple modules. So a minimal module, like the base module, is called as java.base module. So what you can do is you can start creating your applications, first of all, which it could be modular, and then you can start defining that, oh, my application really depends on those specific modules. So the base module in that sense, java.base, which basically corresponds to a few packages that it already allows for you, may be enough for most of the applications. So what you can do is you can take a look at the tool called as JDeps, which is part of the JDK itself, and you point that JDeps tool to your jar file, and then it'll automatically identify the dependencies on the modules that are available for you. So with JDeps, you can identify the modules, and then there's a tool that you can use to create a custom JRE. So let's take a look at that. So JLink is my tool by which I can create actually a custom JRE. So what I'm saying is, JLink is my tool. I'm going to give it a module path. And in terms of the module path, for example, I could have, by default, it is in Java home/mods directory, where all my modules are living. And then I can say, add only this module. So I could, for example, say java.base module. And then what that gives me is a custom JRE. That custom JRE is only for me. The important part to understand here is, I don't need to modularize my Java application for this. I can take an existing application and then still create a custom JRE using those modules. Or if I have already modularized my application per JDK 9 onwards, I could still say, bring that as a module as well. So you're truly modular in that sense and leveraging all the benefits that come along with it. Now, that custom JRE, I'm giving a name, let's say --output hello JRE. I get that custom JRE, and then I can say, within that hello JRE, I got bin Java, and then I can say the module, because my module name in this case, when I created my application, was hello world. So I'm pointing to that hello world module, and then I just say, run the class. Because when you're creating the module, essentially, in that you have a module info.java, in which you can say, here is my class that needs to trigger up. So all this kind of becomes a very nice, contained environment, so to say, specifically for your Java applications. How can we apply that concept? There's a concept of multi-stage Docker file in Docker. And the whole idea of that is, typically when you're building your Java applications, let's say you're a Maven developer or a Gradle developer, you'll say Maven package. And then maybe you can use a Docker Maven plugin, which would generate a Docker image for you. But anytime you switch between tools, to me, that's a leaky bucket. That means there's a hole in the bucket and the water is going to leak out, and the bucket is never going to be full, because that's my goal. So in that case, multi-stage Docker file works really well. So in this case, what I'm doing here is I have a Docker file. In a Docker file, I've defined multiple stages. And what you can do is you can do a handoff from stage 1 to stage 2 to stage 3, and so on and so forth. And then you have your last stage, which is what is really firing up the container. So in this case, if you take a look at it, I have the first stage where I'm saying my base image in this case is OpenJDK. I'm using 10-JDK as a tag over there. I'm using JDK as a base image over here. Then I'm defining the work directory, which is JLink output directory. So basically, all the commands now going forward are executed by base as part of that. And because I'm using OpenJDK as a base image, I have the JLink command available to me automatically. And I'm saying the module path is Docker Java home. That is by default coming as part of the OpenJDK image. I'm stripping the debugging information. A lot of the times when customers are building their image, they don't realize there's a lot of debug information that is available as part of the runtime. If you don't need that, strip it out. That, again, constrains your image and makes your image much smaller. So, and then finally, I'm saying output. So Java is basically my custom JRE in this case, and I'm adding the modules over here. Stripping the debugging information, again, is critical. Think in the terms of microservices. When you're creating those microservices around the world, you don't, and if your cluster is dynamically shrinking or growing, whatever is happening, if the image needs to be downloaded, the image size needs to be really lean, and it really needs to contain only the components that matter to you in that case. So that's where the strip debug becomes very handy as well. And I'm further compressing the class file as well. So there are commands available with JLink that allows you to really start shrinking your image size. Finally, I'm saying, OK, I'm using an operating system. Here is my work there. And the fun part here is where I'm saying copy from. And the from is my previous stage of the multi-stage Docker file. I'm taking that Java build. This is the output directory. Set up the path, and fire up the command. I mean, in this case, it's just going to open up a bash shell for me. But I could have very well used that custom JRE to fire up my command and execute it. So think about now, anything that's happening in the first stage is not preserved as part of the image. So your image, what is really created, is only taking the output from the first stage. So think about doing, instead of using OpenJDK, you could also use Maven as the base image. And then you can say Maven package, and then it's going to download all the dependencies or download the internet in your Docker image. But that stays out of your image when the final image artifact is produced. So you caught your image using your standard build tools, but using Docker as the facilitator for those tools, as opposed to downloading Maven, configuring it, and M2 and repositories and all those things. You can just download it, and then you can say, here is my base operating system. Grab that target output.war, drop it in here, and dump it. Or maybe using Tomcat and deploy your applications over there.
Thanks, Arun.
Yeah.
Now that Arun explained how to generate some of these smaller images, I want to share with you how much you can benefit from using these tools. By default, the JDK is not JLinked. It's got every module in the Java runtime, and it's about 568 megabytes for a Linux x64 image. If we just use the minimum module, Java base is the requirement. That's the smallest module, smallest image you can create. You can see that it's 46 megabytes. So you do benefit immensely from customizing your Java runtime to use the modules that your application requires. You can see in this chart that with Netty, you can get an image down to 60 megabytes by just selecting the modules that it needs: Java logging, Java management, and JDK unsupported. It doesn't include the Netty application itself, but this is the Java runtime required to run this Netty application. There are other options in JLink. There's JLink plugins that do things like strip debug information, line numbers that will actually allow you to create an even smaller image. If you use compression, you can get 25% smaller as well. But just the Java runtime is not the only thing that's consuming space in your Docker containers and Docker images. The base image is a critical issue as well. As you can see, we've made some attempt at Oracle to produce a slim version, which drops the Oracle Linux size down from 229 megabytes to 118 megabytes. And you can select any image you want as long as it can run Java. You can pick Debian, Ubuntu's, and there are probably hundreds of base images that you can use that can run Java, as long as they meet the minimum Linux kernel requirements. There is a really small base image, Alpine Linux, that uses a different libc, and it's a very lightweight kernel. It's called Alpine Linux. I'd like to just take a poll. Anyone here using or want to use Alpine Linux? I'm trying to get a sense for how important this is. Well, that's quite a few. It's almost like 80% of the audience. Well, we have a project, OpenJDK project called Portola, which is a port of Java. Because they use a different libc, we have to port Java to this particular version of libc and take some of the kernel differences into consideration. The Alpine Linux base image weighs in at a lean 4 megabytes, which is really nice and small. We made changes to support the Musel C library. The links are here. If you want to take a look at the project, download it, build it yourself. We do have early access binaries on Java, jdkjava.net 11. We do not have, at least at this time, a final official tested release, but we see that there's a lot of interest in Alpine Port here. I would like to, query the audience. If anyone's interested in helping to complete this port and get it integrated into the Alpine download images, by all means, send me an email. You've got my Twitter, at Bob Van Det. We'd love to get you involved to help make this happen and to ensure that Alpine is supported. So you can see with an Alpine Linux image, we can get down to 50 megabytes with the base image and the small Java runtime. That's quite a lot of savings. I'm now going to get into some Docker features, Java features that we've done. They're general purpose features that Docker benefits from, and then I'm going to get into some features that are specific to Docker that we've done in the last couple of releases of the JDK. So microservices, function as a service, they all encourage lots and lots of images and containers to be running on the same machine. Every year the amount seems to go up. I went to the container conference, CNCF conference, and they showed a chart. The average was 250 containers running simultaneously on a host, and that's expected to grow next year. So this encourages the savings of memory and savings of disk and producing these smaller images. So we've taken care of, with modules, the Java runtime, and we have some nice small base images, but what about other data that we load up into memory and it's read-write, so it's unique to each container? And one example of that is a Java class data. Well, we have some technology that's been evolving over the last few releases of the JDK. It started out as class data sharing, where you can take and create a shared library that can be shared across containers. And it initially started out where we only supported the internal classes and packages for the JDK, but over the last few releases, we've extended it to application class data so you can get even more sharing. This allows you to start up faster because we pre-digested all of that bytecode that we have to process, and you save a lot of memory. As you can see in the left-hand side, we're saving about 30% of our startup costs for the WebLogic server. And in the right-hand chart, you can see that you're sharing more memory. You go from 20 megabytes to 66 megabytes of memory that's actually shared between two containers. And obviously, if you have 200 containers, you're sharing a lot of memory. So that's for class data, module data, but what about the code cache? When Java starts up, we compile lots of methods, and that's, again, in read-write memory, which is unique to every container. So to attack that problem, we've come up with, it's currently still an experimental feature, but it's ahead of time compilation, where we allow you to use this JAOTC tool. You feed it a list of methods that you want to generate into a native library. And again, this native library can be shared between two containers or as many containers as you want. It helps to speed up startup because we're not spending all the CPU cycles just compiling these methods. So the next set of features are things we've done specifically for Docker and C groups. The JVM does a lot of ergonomics when it comes up to try to adapt itself to the host that it's running on. We look at how much memory, how many CPUs you have, and in Docker, you can actually specify those things in a container. And in the early days of Java, we weren't honoring these settings, and it wasn't transparent, so we actually had to make modifications to the JVM in order to take advantage of that. The first set of resources are the CPU resources. There are 3 different ways in the Docker run command that you can specify how many CPUs you want to use to run your Java application or your container if you're not running Java, but we hope you're not. The first one is the CPU sets. That says, give me these physical CPUs, and those are the only CPUs that I'll run on. The next one is CPU quotas and CPU period, which limits the amount of time you get per time slice in the operating system scheduler. In The last one is CPU shares, which you give a relative number. I want more priority over this process versus another process that may have a lower share count. And all of these things affect how Java tunes itself. And as you can see, in JDK 9, we added support for the CPU sets. In JDK 10, we've added CPU quotas and CPU period support. The run --CPU S option, all that does is it translates into a quota and period setting. So it's really the same from our point of view. The one thing to note is that container management software can actually use all of these things at the same time. So it made it a real challenge for us to come up with a single number to return in the Java API runtime available processors that we use to set up the fork join pool and some of our internal compiler threads and garbage collecting threads. And the next slide talks about the algorithm that we finally settled on that works quite well. So the algorithm basically is to take the CPU set count, since it's a hard number of CPUs, we will never try to exceed that number. But if you specify both the CPU quota and CPU period, we'll actually use the CPU quota calculation, the quota divided by the period, in order to determine how many processes we should dedicate to Java. In the event that you want CPU shares to be the driving force for whatever reason, we've added a flag, prefer container quota for CPU count, that you could turn off, set it to false. This seems to work well. We found that Kubernetes actually uses CPU shares and CPU quotas. They specify CPU shares as the requested number of CPUs I want to dedicate to this container, but they use CPU quota, which is the hard time limit, as an upper limit to allow bursting of that container. So we had to take this into consideration in coming up with this algorithm. And this algorithm is actually updated in JDK 11. In JDK 10, we always just took the smallest number for the 3 different settings. Oh, by the way, if you don't like what we've done, we have an XX flag for you as well. Active processor count, you can specify whatever number you'd like to dedicate to your container. Now we're moving on into another resource category, memory. Docker -- memory allows you to specify how much memory is dedicated to the container, and we need to know that in order to set up the heap size and other VM internal memory sizes for running Java programs. So in JDK 10, we added support for that. We also added some additional flags to let you specify the percentage of the memory that's dedicated to the container that we should set for the Java heap size. This allows you to say, I want 70% of the memory that's in the container to be in my Java heap, so that you don't have to hardwire --XX, set my heap size to this value. It allows Kubernetes to specify memory limits, and we will automatically adjust and give you that percentage. If you'd like to find out what decisions we've made, we've added some logging support, -xlog, OS plus container, and set it to trace in order to get the maximum output. And there's also a great blog that you can go to, I put in this slide deck, from Matt Gillard, who is in our FN team. It explains this stuff in a lot more detail. And finally, we've had to improve Java in a few other areas in order to take advantage of, to solve the problem that C group processes, the PID that we see within it is not the same as the host, so that we can properly detect Java processes running on a host from a Java program running inside the container and outside the container. So we fixed a few problems there. And I just pushed to fix the RFE for container metrics this morning. It's going into JDK 11 and will allow us to extract the runtime information about how much CPU time you're using, memory you're using, what's the maximum and minimum, so that we can add that in the subsequent Java release to our Java Flight Recorder performance analysis tool. And we will add an MX bean as well. And we're also in the future going to look at using the NUMA information that's available in the container to allow the GC thread to optimize for the memory system layout that the container has. And with that, that's the end of our presentation, and we actually have some time for questions. Yes.
We have.
Do we have a mic? Do we have to
running?
pass?
We have a runner. We've got plenty of time for questions.
Yeah.
Hello?
On Kubernetes, let's say you're doing multiple apps. Are there any tips or tricks for, say, using a shared volume with common dependencies so that you can get things down even smaller with your images? So multiple apps, one pod.
If you're layering the creation of your image and put the Java runtime in that image and do some of the things like class data sharing and ahead of time compilation, since they're shared libraries, as long as they're on the same file system, they will automatically be shared between the containers. I think it's JDK 12, we're actually going to be layering the application class data sharing libraries. So if you have two different applications that use the same Java runtime but have unique classes, you can just add that incremental shared library for the second and subsequent applications to get the maximum sharing. That's not this release, but it's coming in the next release. Shared volumes is another way to do, to share as much as possible, but you have to be careful, make sure that the Java runtime that you might create with JLink can support all of the applications that you want to run.
Hi, amazing talk, by the way. I have a question regarding the first part that Arun mentioned, Docker files and JDEP and JLink. In order to run the first part of the multi-stage build, you need to do JDEP before actually running that part, right? So it means that I still need to have the JVM on my machine with JDEP, with Maven, so I can basically pre-download everything that the container will need. So is there a way where I can just clone a repo and do Docker build without having to have the JVM installed on my machine and all that stuff?
Right. So you should be able to, if you're using OpenJDK as a base image, that itself has a JDEPs tool in there.
Yes.
So you should be able to use that as the tool by itself to figure out what your dependencies are.
Yeah, but still, if I do that, every time my code changes, JDEP will need to run again, so the multi-stage build will need to run from the very beginning, and that will make it take a lot of time in the CI/CD pipeline, right?
Well, JDEPs doesn't take that much time at all to run. It simply, reads through it.
Is the question more around Maven or more around JDEPs?
It's more about bundling the whole application into the container. So basically, my ideal experience would be someone just give me a repo, I clone it, and do Docker build, and that's it. I don't need to even have the JVM on my machine to build a container.
Well, I think even when you're building it, if you're using OpenJDK as a base image, you don't really need the JVM on your machine per se. Yes, it becomes one of the layers over there.
Yeah.
Yeah.
Okay. Great. Thanks.
One more.
Hi, great presentation. Thanks.
Thanks.
Do the JVM improvements also apply to other JVM languages besides Java? Something like JRuby or any other number of the JVM languages?
Well, any of the layered languages that run on top of the JVM will take advantage of the work that we've done. I can't speak for their products, whether they are doing something under the covers and working around us. But I know that we're reporting the runtime available processors and the amount of available memory in the JVM to any application that's running on top of it. So it should automatically transfer to anyone using our newer JVMs, our JDKs.
Great presentation. Question number one, slides are going to be available?
Yes,
Okay.
I'll share the slides on my Twitter account.
Great. So question about the memory limitation in context of JVM and Kubernetes. So one of the problems we had on big RAM machines, native memory, Java native memory could be in gigabytes, which could go over Kubernetes limits. So are those options, new options for JVM, are they also affect native memory limits?
No, with JNI, people can allocate memory and we can't detect it.
I'm mostly, so by default, if you don't specify size of native memory, if you don't limit it, it's calculated from the available RAM. And it could, I believe on 64 gig RAM, it's like JVM dedicates like 3 gig for native memory. By default, there's some formula. So But if if you don't specify it, and you don't account into your Kubernetes resources and limits, your pod could be easily go over and got OM killed.
You can absolutely run out of memory. We're trying to at least control the amount of memory that the JVM uses for its purposes.
Yeah,
the Java heap, for instance, what the size of our code cache is, and the thread stack sizes that we create. But outside of the JVM, we can't control what people do with malloc and free, right? And so yes, you can run out of memory, and you would probably get an out of memory kill. I highly recommend you fully test your application to make sure, especially when you're playing with some of these knobs where I can allow you to specify 60-70% of the native memory to be dedicated to the Java heap. You could easily run out of memory by starving other native memory allocations that are occurring outside of the JVM.
Okay, let me rephrase the question then. So when I specify memory into Docker,
yes,
is it going to affect all parts of JVM memories or just heap? Or
it's the Java heap and the code cache and thread stacks, the things that we allocate.
Is a JVM namespace as opposed to the user namespace?
Correct. Yeah, unfortunately, when Docker run specifies -- memory, it does not update a lot of the same proc file system information files. Meminfo, if you look at that inside of a Docker image, it shows the host memory, which is the problem that we had to solve here. So I have to fish out the C group file system and the specific file that contains the right answer and provide that to the JVM. I wish the Linux kernel guys just did the right thing. It's like any place that you expose the memory size and Docker specifies it, make sure it's right, but they didn't, so we have to work around it.
Fantastic presentation. I'm really excited for a lot of this. I'm wondering, are any of these features or anything similar coming to JDK 8?
I knew I was going to get this question. There's actually a sustaining proposal inside of Oracle to backport most of, if not all of these features to JDK 8, but I can't give you a firm commitment or a release number that's going to show up. It's currently in testing with some internal applications to see that it actually works. I suspect that before the end of the year you will see it, but I can't guarantee it.
And with the JDK 8 as well, with a certain update release, I believe 151 onwards, there were features added that would honor the memory requirements anyway.
Yeah, the CPU set fix is already backported in JDK 8, I believe, and the memory, there's a XX flag, I should have probably put it up here, that allows you to specify at least the Java heap size based on the C group limits. But the CPU shares and quota fix, that has to be backported, and it's in process, and I think it's going to happen, but yep.
Hey, since there's already an Alpine tag for the OpenJDK image, I was wondering how that's going to, or how Portola is going to differ from that tag of the OpenJDK.
Which tag are we talking about?
The official OpenJDK image has an Alpine variant tag. So I was wondering how that's going to relate to the JDK 11 Portola effort.
I'm sorry, but I don't know the answer to that question. I think the OpenJDK Alpine tag is not done from Oracle, right? I think it's from the Alpine team, and they control that.
Yeah. Okay, so that's going to be
really a question for them.
Okay.
But you can download the binary early access, JDK 11 bundles in that URL that I posted, and it's the latest.
All right, I think that's about the time that we have. Thank you very much. Hope you had a good time.
Yep. Thanks.